Hi, everybody. Let's allow for another 2 minutes for people to join.
No, Dirk has not cloned himself. So the second instance of Dirk is Dave.
Well, the other one looks much better.
I'm trying to change my name in the chat in the participant list, and it seems you can't.
Yeah, I had to do this for other IETF meetings I had to attend, and they didn't want me to join as ICNRG. So sorry.
So why was there a WebEx sent out with a different WebEx meeting? That was the one that was in my calendar.
I suspect this got auto-generated. I'm not sure, or maybe we just had to.
All right. Well, okay. Todo-san and Yuki-san have joined here, so everybody who was in the other meeting is now back here.
Okay, great. Thanks. Okay. Let's get started. Thanks for making this. We know that everybody has a ton of online meetings these days, so really appreciate you being here. Yeah, welcome to ICNRG. So this is an interim meeting after IETF 109. So Dave and I are sharing that. So while we do this intro, you can already think about whether you would be able to help with taking notes today. So we're still looking for a note taker, and it's kind of important. Okay, so this is the online participation section that not everybody has received. Sorry for that. Let's do the Q&A using this protocol. So add yourself to the queue if you have a question using +Q. And quickly take note of the IRTF note well. So this has to do with IPR, and so by participating here, you agree to follow the IRTF processes. And this is mainly about notifying the community quickly when you are aware that, say, IPR relevant topics are discussed that you know of. We also have a privacy and code of conduct, and there's also an anti-harassment procedure. Please take note of that and yeah, adhere to these code of conducts. And then again, as usual, we are here in the Internet Research Task Force. So we are generally interested on longer-term research that is related to the Internet, evolving the Internet. And so this is clearly research, not standardization. And sometimes this is irritating because we are using similar procedures or concepts on drafts and RFCs. Just be aware that we're not doing standards here. Okay, if you're new to this is our general infrastructure, mailing list, wiki page, and yeah, so no, I hope everybody has had enough time to think about volunteering for taking notes. Do we have anybody?
I usually do it, but this time I can't because I'm actually in double duty and I'm waiting for somebody to come repair the bell here. So I won't be able to be there all the time.
Okay. Yeah.
So sorry, but I thought about it and my heart is with it, by the way.
Yeah, we appreciate it. Thanks a lot. It's also good at time to maybe give somebody else a chance. So you have done it quite a lot. Thank you. 。 So this is just about recording the conversation, the questions and answers. Doesn't require full recording of the meeting.
Okay, let's do something. I'll do it, but I'll listen to, you're recording this, right?
We are recording this, right?
Okay, so I will do it listening to the recording.
Okay, thanks very much. What did you say?
Like, make sure that you send me the link to the recording, and I have to do coin anyway. I have to help with coin.
Okay.
So I'll do it with the recording over the weekend or something.
Okay, I will.
And I'll
Thanks.
try to type some stuff into coding MD, just so we don't miss anything.
Okay, well,
I mean,
I'll look at
I won't
everything.
be able to pay attention to taking notes the whole time because I'm involved in a couple of the
Right.
topics.
So I went over this a bit quickly. So we have this CodeMD link here that I also sent around, and you can find it on the data tracker. Please.
Yeah, it's already in there kicking.
Yeah. And so we're also using this for tracking attendance. So like the online bullsheet. Please feel free to add your name to the list there. Thanks. Okay. And so this is the agenda. Let me make this a bit bigger. So we have a pretty exciting agenda today. So many cool research presentations. So just asking, is there anything you'd like to change? Any last minute requests? So regarding the timing, you can see it's quite ambitious. So you don't have to use all the time in your time slot, of course. But I mean, since this is research, we anticipate discussion. So I mean, we are not constrained by the usual, room bookings or anything else. Okay. Just very quickly, so we went through our documents in the group, and so here's a quick update just of the ones that are currently nearing completion. And well, firstly, let's celebrate the publication of RC 8884, research selections for using ICN in disaster scenarios. This had a long time coming, but we are happy that it finally got published. Thanks again to the authors and everybody who helped getting this done. We have a few other drafts that are so kind of cycling around our group and the IRSG, and so the ICN LOPAN draft, it's also almost finished. So I think we are just waiting for the ISG to agree that it's ready, and we moved on. So we had some revision cycles already. The QoS architecture draft is about to be sent to the ISG for conflict review. So this is basically out of the IETF. Now, these two NRS documents, they also had a few cycles. So we are, I think, waiting for a revision for requirements. And conservation is currently in IRSG review. And then finally, the LTE 4G draft, so that also got some comments in the IRSG, and so waiting for an update on that. Yeah, so this has been really good progress. So despite all the challenges in this year, so thanks everybody for keeping doing this. It's really great to see that this is all moving forward. We have a couple of more documents that I'm not going to talk about today. So let's maybe do this on the mailing list. We will also sort some updates and expect some updates of some of our other documents, but let's discuss them on the list. Unless there's anything we missed, please let us know. Okay, good. Okay, so with that, we can start our technical program, and like to hand it over to Christian. And
okay, you will present the slides.
I don't have your slides yet.
Oh, I sent it by email. Of course, you were talking.
But I
Can
can
you
just
hear them directly?
I can just make you a presenter, Christian, if you
Okay.
like.
Hopefully, I don't lose then my view. It's always a little bit.
Yeah, this is WebEx. You will use your lose the WebEx view.
So, do you see the slides?
Beautiful.
Yes.
Okay, good. So let's quickly go to that. It's not really a technical presentation. It's more kind of where we are, what the different positions or views are. Quickly, a timeline. It all started with the draft. And I saw Chris is also on today's meeting. So where we wrote down that very first initial version, it was in the background some C programming with CCN Lite and getting some experiences on how you program that. Then later, Mark and Dave joined. They have stake in that because I think of the manifests, of course, and the nameless objects needed for CCNX. And that was very welcome to help that draft evolve. And in spring, Mark did some programming and gave another push. Namespace concept came into that. I have collected all the links that he sent in at the end of the slide set. So people interested in the details can look them up there. And I think the most important part to report today is about what happened in August, where we had a lot of discussions. I think it started more or less with mail by Mark, then Cenk joined in, Ken, and then a lot of ping pong with Dave, Mark, and me. One of the additional things were that concept of virtual blobs suddenly came up. And it was interesting to see the discussions that really there is some work still to be done. And I just took one sample of a statement. Flick describes a single file. No, by definition, Flick must always describe two files. So we already at the conceptual level or terminology level have to be careful what we are doing here, and we need some revisions. So quickly, where we are. So that is from Dave. He just sent me that. There is a disagreement on how basic or how complex, how full, how complete the spec should be, the scope. There is an agreement that we should have a kind of extension, so future-proof properties. The namespace thing is mentioned that Mark came up with, and metadata capabilities, so you can easily traverse the tree, find things easily in a hash tree. And well, exactly how that metadata machinery would look, that is exactly something to discuss. So we are in the plane of that discussion. I quickly switched to Mark's assessment. I realized he made a contribution in September, options for Flick name constructors, and I think there was no follow-up on that. So that is also an ending discussion we should pick up. On the Flick document itself, similar like Dave, we need name constructors, so that is the name space concept. The extension of manifest is not really contested. How the link section should be done, that needs a little bit discussion. The format. So the question of it's not complex or not complex enough, he more says the current thing is not too complex, so why not go with that? So that is the state. If I can also add my position, I did a detour recently on looking at existing software called Hypercore, a protocol that is information-centric in the decentralized community that has an access protocol, and it has an interesting constructions also using immutable data blocks, hash pointers, signed Merkle trees. So it has a lot of the elements Flick is about, but they use it differently at a higher level. They build higher level data structures, file systems, for example. And I think we can learn from that. It can inform how the Flick scope should be, how to have a toolbox to do exactly such high-level data structure. So of course, I try to get here arguments for a more incremental way and maybe decomposition of the Flick document. But that is pending discussions. There is also, that's not necessarily the truth to aim for, to look at hypercore per se, because they don't have really manifests, but it can hopefully help to give a perspective on the discussions we are having. So summarizing, I think Dave, Mark, and me, we definitely agree that we should participate in more of the technical discussions. I'm not sure about Chris, maybe he can join in. He is now also on that call. Here are all the links, the references, where I think we should continue working. And I would like to invite Dave and Mark to complement what I have said.
So I'll chime in for a second, which is we tend to go in fits and starts on this. So I think our high order goal ought to be to freeze something we can push through and get to experimental. Because I think the lack of something stable is probably limiting people's interest in actually using manifests in major ways to solve some of the perennial problems we have. So I think I'd like to try and set a goal of getting this through RG last call by mid-January. I don't know how other people feel about this. So we may wind up taking a bit of an axe to some of the more popular fancy things we'd like to do in order to get this through. And remember, since this is an experimental draft and this is a research group, there's no reason why we can't move this to multiple versions as long as we get the extensibility and versioning capability right pretty fast. I'm done, by the way.
Yeah, okay. Is Mark joining? Or no, I think he had a time conflict, right?
Yeah, Mark couldn't make it, unfortunately.
Right. And Chris, do you have something to say here?
Nope, this all sounds good.
Okay, so I think the four of us should reconvene and see exactly how to take the axe and do something. Okay. Dirk, is that fulfilling what you had in mind with that status update?
Yes, very much. Thank you, Christian. It's
Okay,
great.
welcome.
Yeah, so
I'd like to chime in that there's no, this isn't a design team in the sense that other people are not encouraged to join us in working on the technical aspects of this, right? We are not oversubscribed in people's input by any stretch of the imagination. So folks, please take a look at the, the notes and the draft, and you have ideas to contribute and particularly help on solidifying the draft. That's obviously something we would very much appreciate.
okay, great, thanks. Edmund, shall I make you presenter? Is that okay?
Sure. Sorry, I was muted.
So it should work now.
Okay, so I don't see a share button yet.
Should appear on the bottom toolbar next to stop video. And I think you should.
Okay, let's see. I have to do, sorry, so I have to adjust the system setting here.
Yeah, take your time.
Okay, I just allowed it, but it still doesn't show me the button for some reason.
Okay, so
Um,
Webex thinks you are presenter.
yeah, I mean, it tells me to open system preferences, and then I changed it, and then it's still not giving me the choice to share the screen. Let's see.
Is it a permission issue, perhaps?
That's right. I just gave it permission, I think. But, okay. Okay. Yeah, so maybe we should just have, I mean, if you don't mind driving the slides, I don't want to hold everybody up.
Sure, I can do it. Yeah.
Yeah, so I have the bullets come in sequentially, but you can just basically like hit all the bullets in one page, have them show up at the same time, so we don't have to. Yeah, sorry about this.
But Dirk, can you enlarge the slide space? It comes up very small on my screen. I don't know if it's everyone. Yeah, thank you. Small font for old
I can go
eyes.
up to 5K. Okay.
Okay, is that big enough for everyone?
So I can't see it. You have to tell me if it's too small.
Okay, I mean, it's fine for me. Okay. All right, so very nice to be, sorry, it's very nice to be a part of this discussion. Thanks for inviting me, Dave and Dirk. So this is about a few projects which have, two projects actually, which have been taking place the last couple of years on using data-centric approaches to look at data-intensive science areas. And so this encompasses a lot of very important science areas, such as Large Hadron Collider. This is for high energy physics, which has been responsible for many famous discoveries, including Higgs boson, for instance, many Nobel Prize discoveries. Large Synoptic Survey Telescope is another application that is going to be the next big thing in astronomy. Square kilometer array is another project in astronomy, astrophysics. Genomics is another application. So these are all scientific domains and applications which involve many scientists around the world, involving enormous data volumes, and have very common needs in terms of data delivery, distributed computation, and what these projects are about is using a data-centric approach to solving these big data-intensive problems within these areas. So next, please. So these data-intensive applications face a similar set of problems. So I mentioned there's high energy physics, LSST, LIGO is gravity wave genomics. So the system challenges having to do with how to index data, how to secure the data, how to store the data, how to distribute the data, how to analyze the data, and how to learn from the data. So these are very common themes that run through all of these different areas. And all of these things, these tasks, these problems have to be, tasks have to be accomplished using coordinated use of computing, storage, and network resources. And these resources, while they are getting more abundant, they're still limited. And the rate at which the data volume is increasing is still far surpassing the rate at which these resources are increasing. So now what's happening right now, and after, of course, collaborating with many people in the physics area and also now starting in the genomics area, we found that these different domains are dealing with similar problems. However, they're basically solving their own problems in isolation, more or less. Each of these domains is developing their own solutions, which tend to be incremental because these experts are not networking experts, they're domain science experts, and a lot of efforts tend to be replicated across these different domains. And one may ask why that is, why we have this problem that you have this replication of efforts and incremental solutions. Part of the problem, I think, that one can identify is this gap which exists between the application needs and the existing networks and systems. And so I don't think I need to convince people here that we have this gap, and the applications are really they're really caring about the data, whereas the networks and systems tend to focus on addresses, processes, servers, connections, and the security solutions also focus on securing the data containers and delivery pipes. And so because of this gap, these domain experts have to basically cook up their own ad hoc solutions to meet their data needs, given their existing systems. And this has caused to this kind of situation that we have today. Next, please. So what we're doing in these projects is to take a data-centric approach to system and network design, and providing system support through the whole data lifecycle, from the production of the data, naming the data, securing the data directly, to delivering the data using names, and enabling in-network caching, for instance, is a very big key functionality that's required by these applications. Automated joint caching and forwarding, multicast delivery, all of those things which are enabled by a data-centric approach. And the key is that we're trying to adopt a common framework to support these different application domains, come up with a common structure and way of looking at things, so that these different domains can draw from this framework and build systems which can meet their needs. And so this, of course, has been motivated and inspired by NDN project. Next, please. So we got into this a couple of years ago when Harvey Newman, who's a very well-established and well-connected physicist, high-energy physicist at Caltech, actually approached me because he had heard of NDN and said, why don't we try to use NDN to speed up things in the high-energy physics network. So this was a great opportunity, and we started collaborating, and we applied for this project, which was thankfully it was funded by the NSF back in 2017, called SANDY, SDN Assisted NDN for Data Intensive Experiments. So the PIs were myself, Harvey Newman, and Christos Papadopoulos at Colorado State. And then because he had gone to DHS, the project was taken over by Craig Partridge. And this project has been, I think, very fruitful, and it has been supported by the other LHC sites, as well as the NDN project team. So the approach here is to use NDN to redesign the LHC Large Hadron Collider High Energy Physics Network and to try to optimize the workflow. So what are the main things we did? We developed an NDN naming scheme for fast access and efficient communication in HEP and extensible to other fields. We deployed NDN edge caches with SSD at multiple sites which are connected to the high energy physics network. And we looked at simultaneous optimization of caching of hot data sets and forwarding. Hot data sets or data sets which a lot of different scientists tend to access in the high energy physics network. Next, please. So what are the results from SANDY? So this has been going on for a few years. The feasibility of an NDN-based data distribution system for LHC was first demonstrated at SC, the Supercomputing Conference, in 2018, where we actually demonstrated a system which had a redirector from the system which directs requests within the HEP network called XRD. It redirected these XRD requests to an NDN-based system, which would deliver the data back. And so that was demonstrated at SC18. In SC19 last year, we showed a greatly improved throughput and delay performance. And it had three major components in the implementation. One is the joint caching and forwarding algorithm that we developed in Northeastern called VIP. We actually coded that up and implemented it within this high energy physics network, or this testbed network that we put together. We also integrated that with the high-speed NDN-to-BDK forwarder developed by NIST, and that they actually finished the development very shortly before the SC19. It was quite a development effort to integrate these two things, but thankfully that was successful. And then there was an NDN-to-BDK-based consumer and producer, which was developed by Caltech, or also around that time. So all three components were put together for this demo. And this demo took place over a transcontinental layer 2 demo testbed, which ran from the SC19 demo floor to Caltech, Northeastern, and Colorado State. So this involved, of course, working with a lot of partners in Internet 2, ESNet, and CNIC, and so forth, to just put together these VLANs at layer 2 to put, and this in itself, of course, required a lot of work. So this was an actual demo over a wide area network live demonstration. And it was taking place, with two NSF PMs sitting right in front of us. So we really had to make it work, and thankfully it did. So we achieved over 6.7 gigabits per second throughput. This is single thread implementation between the NDN-to-BDK based consumer and producer over the wired area network using NDN. And we also, so that was the throughput performance. We also used the optimized caching forwarding algorithms to decrease download times by a factor of 10. So this was quite a success from our point of view after a few years of development and implementation and integration. Next, please. Yeah, so this is just a screenshot of the throughput which we obtained. So if you could look at the upper left hand corner there, you see the 6.71 gigabits per second. This was photographed on the floor there. Next, please.
And then one real quick question.
Yes.
At 6.7 gigabits, what was the bottleneck?
The bottleneck. Yeah, I think the bottleneck was I think the forwarder, basically. I mean, the forwarder, if this performance is very much in line with the what the forwarder performance that was obtained by NIST in their testbed, using, of course, they went to multi-threaded implementations, which increased the throughput linearly, actually, with the number of threads. So this was a single-threaded implementation.
Thank you.
Yeah, sure. Yes. So yeah, so that was Sandy, and that was Sandy is actually still running in its last extension year, but just this October, we received another grant from the NSF called Andes. It's called Andes, like the Andes Mountains. NDN for data intensive science experiments. So this, you could look at it basically as an extension of the follow-on to Sandy, because Sandy is ending. So now the team is with Northeastern, with myself as being PI, Caltech, Harvey again, and UCLA, where Lisha and Jason Kong are the co-PIs. And at Tennessee Tech, Susmit Shanagrahi, who has become faculty there recently, and formerly was with Christos at Colorado State, is a co-PI. And So what is this new project about? Well, it's about basically pushing the envelope further on this project. So we have big challenges coming up for LHC. LHC data volumes are to grow 10 times due to high luminosity LHC, which is coming in 2027. We also have greatly increased data complexity due to that high luminosity experimentation. We also, this project is also going to look at the genomic applications, the human genome data and the Earth biogenome data is hitting the exabyte range. Okay. And also in this project, we're going to focus more on the fact that we have to need to use diverse computation, storage, and networking resources. Basically, you have to use everything that we have to accomplish the task we want to accomplish in these applications. So the approach is to build a data-centric ecosystem to provide agile, integrated, interoperable, scalable, robust, and trustworthy. That's a lot of words there for heterogeneous data-intensive domains. So let's talk about some of these things which we're going to do. Next, please. So the goal is to deploy and commission the first prototype production-ready NDN-based petascale data distribution, caching, access, computation system serving major science programs with the LHC high energy physics program as the leading target use case. And with biogenome, human genome projects, as well as the LSST SKA projects as being future use cases. We're going to leverage NDN protocols, high throughput forwarding caching methods, and containerization techniques, and integrate it with the SDN, some of the SDN methods that Harvey has been working on, and as well as FPGA acceleration subsystems, where Jason Kong has a lot of expertise. So this is it's got a lot of ingredients that would make the system much more high performing. The goal is to deliver LHC data over a wide area network at throughputs near 100 gigabits per second and dramatically decrease download times by using optimized caching. And we're going to have an enhanced testbed. So this is going to build on the Sandy testbed with more NDN data cache servers to fill out the Andes testbed. Next, please. So some of the research agenda, just to be a little bit more specific, we're going to, so in order to increase the throughput towards 100 gigabits per second, we're going to look at multi-threaded consumer and producer applications and aim for linear throughput scaling. And this was evidenced by the experiments at NIST on the DPDK forwarder. And of course, now we have to build the consumer producer applications as well as look at the multi-threaded versions of the caching algorithm, caching and forwarding algorithms, combined caching forwarding algorithms. We're going to look at containerization in order to deal with diverse server equipment and interfaces, specifically to use Docker containers to host guest OSs for state restoration to ease upgrading. We're also going to look at data integrity and provenance. So as an immediate goal, we're going to look at data origin authentication. So in these high energy physics applications and these data science applications, security is not a foremost consideration at the moment because they basically keep access to these systems to be very restricted. You have to apply and you wait a long time to get approved. Once you get in the system, you're in the system. But I think the authentication of the data is still extremely important. And so we're going to start with that and look at the use of data manifests for data authentication, which is something that NDN, of course, is very good at. So we're going to start with that. Later on, as we go along with the project, and later in the project, we would also possibly look at provenance tracing, which is the idea that data is going to be, the output data of the one researcher might be used as the input data for the next researcher, and so it's very important to trace the provenance of the data. But that's going to come later in the project, and possibly. Next, please. We're also going to look at congestion control and retransmission. This is something that Sandy did not have that we're going to actively look at. And there's, of course, a lot of things to draw on in that respect from NDN. We're going to look at multi-threaded caching forwarding, optimized caching forwarding for the BIP algorithm. And we're going to look at hierarchical caching systems. Because of the data volume that's present in these applications, it's just not practical to simply look at RAM. So one has to look at all kinds of storage one could get your hands on economically. And that involves SSDs, Intel Optane, et cetera. But then, of course, all of these have different read and write speeds. They have different durability and so forth. So one has to take that into account in any kind of caching algorithm that one develops. So we're going to actively look at that. And then we're going to look at, as I mentioned on FPGA acceleration. So these are, of course, being used. They've been suggested that it be used for forwarding, name-based forwarding in NDN. But we have a specific way we're going to use it here in this project. Basically, in the NDN DPDK forwarder, there are these tables which are used: the name dispatch table, the combined PIT CS composite table, and the FIB. And a lot of these lookup functions and the hash functions will be accelerated using FPGAs. Jason Kong is going to lead the effort in doing that. We're very hopeful that this FPGA acceleration can give us a lot of performance boost in this case. Next, please. All right, so just to conclude here, this was kind of a really short tour of what we've been doing. So data-intensive science applications require fundamental networks and system solutions to address very common needs. And we believe that NDN provides a data-centric system support through this whole data lifecycle is a very good fit for data-intensive science, as a natural fit for LHC genomics and other data-intensive applications. We have shown in the Sandy project already a high-performing NDN system with a throughput of 6.7 gigabits per second, demonstrated live at the SC19, using the NDN DPDK forwarder as well as the VIP optimized caching and forwarding. And with the new project Andes, we're going toward the first prototype production-ready NDN system, integrated with FPGA containerization, with support of SDN operations that Caltech has been looking at. And we're very hopeful that we can build a very good system for high-energy physics, genomics, and by leveraging that, we seek long-term collaboration with other domain sciences and to develop this common framework which would work for these data-intensive applications and work with many other communities. All right, thank you.
Thanks a lot, Edmund. Super exciting. Are there any questions?
We have a question on the traffic style that we will be using NDIS. Is that elastic or inelastic?
Yeah, good question. So, we're going to look at congestion control as part of the system. So, I assume that's what you mean by elastic. So it's in these high energy physics networks. It is definitely possible to control the input rate in the sense that basically slow down requests if the network gets congested. That's what happens in practice, so I think the system is elastic basically because the delays actually which are being tolerated over the system is way too big actually, sometimes on the order of hours and days. So because these are really large jobs, and so I would probably characterize it as elastic. So I don't know if that answers your question.
Yes, exactly. So it is mostly on the content delivery network facets that you play the game.
Yeah, so it's actually, it's not only a content delivery network, it's also a computation network because you have these computation and analysis jobs that are done over this network. So actually there's a lot more going on than just content delivery. We're focusing on the content delivery as of now, but there is actually a much bigger problem of how to place the computations, how to deliver the data and simultaneously place the computations. That's actually the real underlying big problem.
Good.
Did you see Ken's question in the chat?
Oh.
What is the structure of the data? Single files? And are you doing anything interesting with names?
Yeah, thanks, Ken. Yeah, I didn't have time to go into the structure of the data too much. So it's kind of hierarchically structured. There are the big data sets, and then there are, so unfortunately I can't share my screen right now. I actually had a slide on the data. So there are data sets, there are data blocks, and then there are files, and then there are events. Which they're kind of organized hierarchically. And there is actually a big problem in the sense of, at what resolution, at what granularity you want to do the caching and forwarding, for instance, and the caching is specifically. And we actually did a lot of study as to what granularity we wanted to work with. And it has a lot to do with the popularity distribution, how fast it falls off at different granularities. And we found that at the data block level was where this the fall off was very desirable, meaning you could track a relatively small number of data blocks and be able to capture most of the popularity. So that's where we kind of, the caching algorithms were designed for. And did we do anything interesting with names? So for the high energy physics application, actually, there is a very straightforward, they already have a very well-established hierarchical naming scheme. And the nice thing about high energy physics is that it's a naming scheme which everybody kind of agrees with. And because it's a very hierarchical system. And because all the data is generated by essentially one location, which is CERN, right? So, and so it's not a situation where, you have many different producers of data. So, so there's a relatively straightforward translator which you can build, which translates from high energy physics names to NDN-based names. So in that sense, it's not interesting, but it's also, very good that we have something like that. Now, in the genomics application, it's quite different, and that's one of the situations we're very interested in and also challenged by, which is that in the genomics case, you have static data, but you also have a lot of dynamic data, which is being generated by different players around the world, and they may have very different naming schemes. And so how do we do real-time discovery of new data sets, and how do we adapt, the forwarding and the caching and all those functionalities in this kind of situation is a real challenge. SUSMIT has been working with various collaborators in the genomics area, and he's going to be a key person on this team to take what we have and to generalize it to the genomics application.
So okay, question by Eve.
So yes. So Eve asks, can you share more about what kinds of computation you place in or throughout the network? So there are actually all kinds of computations that go on in these networks because so raw data is actually something that is, the vast majority of the raw data is actually thrown away. It's not kept around because just too much data. And so there's all kinds of initial processing that goes on. And so there are various stages. After the initial processing, there's further processing, and people use, even though they're using the same data, process data, they use their own algorithms, of course, to hunt for particles, right? So so there's a lot of different types of computation that you would have to do over the network. And usually, you have to schedule a certain amount of time on some server, and then you have to pull the data set, and then you have to run it. So all of this actually is being coordinated within this high energy physics network, by clever people, but they're not designed using networking, sort of fundamental networking principles necessarily. So I think the answer is basically that there are all kinds of computation going on. There are filtering operations, there are learning operations, there are inference operations that are happening, and they're being run by different people, and they're all different algorithms, and they have to be situated in different places in the network. So it's actually a very interesting and challenging problem. But just the data delivery part is currently what we're focusing on, but that's already a big piece of the puzzle.
Okay, great. Good. Thanks again, Edmund. Very nice talk.
Yeah, thank you. Thanks for inviting me.
Okay. So next we have Namsong Kyo on broker-based pub subsystem for NDN. And I try to make a presenter again. Let's see how that works.
Okay.
Do you have a share button?
Yep, I can see the share button. Okay.
Cool. Yeah, great.
Okay, can you see my screen?
Yes.
Okay. Hi, this is Namsong Kyo from ICNRG, Korea, and I'm so happy to introduce our research result here in ICNRG. Actually, there are several people involved in this project, and I present this representing them. The title is a broker-based pub subsystem for NDN. Okay. And here's the motivation. The first one is that there are just few pub-sub techniques for NDN, and the most well-known one is based on partial sync mode or pit sync, where you can just allow subscribers request data periodically with long-lived interest. But the problem is that they are not that scalable, and I wouldn't go much detail on that part here though, but they are not scalable enough, and they're mostly can used in enterprise network. And they are limited, especially in low-powered IoT devices. The devices cannot handle a lot of subscribers at the same time. And the second issue is that they are not flexible as in IP-based approaches. For example, wildcard topping matches are not supported in them. So we wanted to design a flexible and scalable pub-sub architecture for NDN. So based on the problem statement in the previous slide, we set up the design directions. First, in order to cope with issues on the low performance producers, we took the broker-based approach, which is commonly used in IP network. And to support scalability, we considered multiple brokers. And also to support flexibility, MQTT-like wildcard topping matches are supported, such as single-level wildcard plus sign and multi-level wildcard shop sign. And we can say that the topics are defined by subscribers because producers just publish data with their names, and subscribers select their topic based on the published data names. So we can say that topics are just defined by subscribers in our design. So in our architecture, we use multiple brokers, which are also called as rendezvous nodes. They do the brokering of publishers and subscribers, as the names indicate. They also store published data for limited purpose publishers. Data can also be stored in devices themselves and other external repositories according to the configuration. And published data names are managed by distributed hash table, DHT, on those brokers. We separated topic management and data management logically. They can be co-hosted on the same physical node. In a topic RN, which we call a topic RN, a topic tree is managed and managed in topic RN, and data RN, data manifest, and data parse are managed. Topic manifest, which is given as a result of a search of a topic tree, includes the information on RNs, which manage data manifest. And the data manifest stores information about where the data is actually located. So we can find more information when you go over the signal flows in the following slides. A service prefix RN is used for this service, PubSub service, in this design, and any publishers and subscribers can reach the nearest broker using the name. And also, each broker has its own name. RN X is a number. Using the number, a specific RN can be reached. We defined the following name scheme like this for data. Data stream name comes first, and then sequence number is followed. For example, for the temperature in room 385 in building 7 in A3, there is the stream name, data stream name, and for the data stream name, you can publish data with the sequence number. And for the command, service prefix comes first. This one, RN, comes first, and command will be followed. The command will be explained in the next slide. And the data name is followed by that, after that. So, for example, RN comes first, and PAP is published advertisement. I'll just explain that in the next slide. And the name for the data. We defined the several protocol messages. There are also commands. So to publish data, publish advertisement, PA, it can advertise the name of a data stream to publish. And publish on advertisement, it can cancel the publish of a data stream. And publish data, it can actually publish a data itself. And subscribe, in the subscribe procedure, subscribe topic subscription, though the name is a little weird, but it'll subscribe to topic to request a topic manifest, and topic manifest will include a list of data RN holding subscribe data streams. And subscribe manifest request, it'll request a data manifest to a specific data RN. And the data manifest will include data names for a data stream. And then the last one is the subscribe data request. Subscribe data request, it will request the data itself to a specific data RN. So each procedure will be explained step by step. So that is the logical separation of topic management and data management. And there are multiple publishers here and multiple brokers. Even if they are logically separated here, but those actually can be co-hosted on the same physical machine. And then publisher 1 and 2 and 3 will publish data with this topic name, topic 2, topic 1A, topic 1B. And when the publisher 1 advertise this topic name, then the nearest RN1 here in this case will hash the topic 2. If it is hashed, then actually it'll indicate that the topic RN is RN1. And for this one, it'll be topic RN4. And also for this one, after the hash, it'll be topic RM4 as well. So okay. Can I go finish, please? Okay. 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 So when the messages arrive to the topic RN, then the topic RN will manage topic 3 based on the names. So in this case, topic 2, and topic 2 is actually came from RN1. And here, if you see this topic 3, then topic 1A is from RN2, and topic 1AB is from RN4. So I already explained that publisher, in this case, publisher 2 will advertise the data stream, this data stream, and if it hash topic 1, then it'll indicate RM4 for the topic management. So it'll arrive to RM4. Then in RM4, it'll insert the name into topic 3. So here in this case, topic 1A is included as came from RN2. And advertisement is also very similar. Besides, it'll delete the topic, the name from the topic 3. And after it is advertised, then real data will be published. So from each publisher, it'll publish data. So the first from this topic 2, the first sequence, the first data will be published. So it will be published it to RN1 because it is RN1 is the nearest one to pub 1. So in RN1, it'll update data manifest. And also data can be stored. Actually, we have several options. Data can be stored here in RN, or data can be still be located in publishers. And also, if there are some other external repository systems, then it can also be stored in the external repositories. So the data manifest will have the information. Data is actually will be stored here. So and also in this case, the first sequence number is was arrived, so it has the information on the data here. On other RNs, they also do the similar similar works. When the data are published. So data are stored and data manifest files for the topics updated in each RN. As I said, data can be stored or data can be stored in other areas like in the devices or the external repositories. For the small data, we actually included data in the interest for the small data. But if the files are large, then data is just published to RN, then RN will pull the data. So we have two separate approaches for different file sizes. And then if the files data are published, then a subscriber can subscribe to the topic. So in this case, a subscriber 1, it'll subscribe to topic 1 with wildcard shop. So it can include topic 1A or B, or if there's C, then C can be also included. But in this case, there are only two topics, two data names, data streams were published. So topic 1 and topic 1A and topic 1B are only included for this topic. So when the topic subscription is sent to RM, then it'll also hash the topic. So it just know that the topics are managed in topic RM4, then it'll fetch the topic manifest, and the topic manifest will have the information about each topic, like topic 1A and topic 1B. So topic 1A is managed in RM2, and topic 1B is managed in RM4. So this is a procedure. You can see that as well. And after receiving the topic data manifest, it'll recast the real data to RM2 and RM4. So it'll recast RM topic 1A and topic 1B to RM2 and 4. Actually, after retrieving data manifest, in the data manifest, it has the information on the data. So in this case, for data for topic 1A, already three, actually from 1 to 3, three data were published. So it can fetch from 1 to 3 from subscriber 1. The same to the RM4, and it is explained. It is very understandable, and yeah, it recasts the data, as I said, after based on the information on the data manifest. And this is the software functional blocks. I think I don't need to go over the details on these blocks, but we implemented our prototype using Python. So there are many utilities. So topic management, and topic can be also managed in try or just press regex expression approach. And there are other utilities, and data can also be managed in memory or Redis or repo outside, external repo. And this software will be open to the public soon after we clean up the software. Even if we finished most of the software, but after cleaning up some bugs and clean up the source, then we'll open the source to the public. And this is a demo. I think it is a bit small, but I hope you can see this. There are three brokers in this case, and this one is publisher, and this one is subscriber. And publisher is attached or is near to broker 1, and this subscriber is near to broker 2. So after starting 3 brokers, then the publish procedure will start. So in this case, 2 name streams will be published, like at 370 room 385 temp, and at 370 room 215 temp. So 2 streams will be published. So if it is published, then actually the message will be arrived in broker 1, because broker 1 is the nearest one. Okay. And it'll advertise messages. So after advertising the first data stream, you can see data stream was arrived here, and then after hashing the topic, it will decide the topic has to be managed in RN3 here. So the message is delivered to RN3 so that the RN3 can manage the topic here. The same for the second data stream at 370 room 215 tab. So if you check the status, you can also provide some utilities to check the three topic management status and data management status in each client. So you can check data, two streams were advertised, and the two streams managed in broker 1. Okay, then if it publish data, so 3 data will be published. So it just arrived here. So 3 data will arrived here. Then the 3 data will be stored in broker 1, and also data manifest manifest file was updated here. For the second data name, so we can check the status, and one data stream was published. And for the second data stream, we also published 3 data. Then we can also check that the 2 data were published. So actually, all the data were stored here in broker 1, and the data topic will be managed in broker 3. So after we published data here, then we'll run a subscriber procedure. So after running the subscriber, okay. Okay. Oops. So, okay. So before running subscription, we can check the status. So we could see the same result as you can see in the broker 1, publisher 1. So 2 data stream were published. So you can subscribe to at 370 with help. So all the data streams with this prefix at 370 to 15 and 385 temperatures will be subscribed. So it patched the topic manifest. So in the topic manifest, you can see those 2 streams managed in RN1. So to RN1, it will cast data manifest. So after patching the data manifest, they can check. You can check that it has 3 data for each data stream. So for this stream, it has 3 data from 1 to 3 in sequence number, the same to this data stream. So then it'll retrieve the data. So we can check the actually check the temperature here, 33 and 29. So there's the simple demonstration, and as I said, this code will be published soon. So we'll announce that through the mailing list to this ICNRG and also Andean community soon. So in summary, we developed a broker-based PubSub system for Andean, and we argue that it is scalable and flexible than existing Andean mechanism, existing approaches. And we're gonna release our code as open source software soon. So that's it. Any questions?
Great. First of all, thanks a lot for bringing your work to ICNRG and doing this nice demo. So you already have a few questions in the chat. Not sure you can see that.
Okay, let me check that. Okay. I see.
So the first one, I can read it to you. It's by Dave. So how is deletion accomplished? So by republishing a topic manifest without the data that you want to delete? And are you using manifest versions for that?
No, we'll just, I mean, as you can see in the advertisement. So this is the published on advertisement. It'll use the same approach like RLN, then the comment published on advertisement and the name for that. Then it'll also hash the same way, so it'll know the topic is managed in certain RN. Then it'll the message will be delivered to the RN which manages the topic. Then it'll search the topic tree using the name. Then it'll remove the topic from the tree. Is
Okay.
it answered?
Can you see the questions or?
Yeah, I see that. Then the second one, where is that?
How are subscribers notified if there's new data in the brokers?
How are subscribers notified that there's new data in the brokers? So actually, I mean, most of you already knows that. I mean, in Andean approach or in ICN approach, it is pool-based. So we have to check that periodically if we wanna, know there are new data. So we have to check periodically.
Okay.
And the next one is brokers introduce the central listing and thus fragile element into the system. Can its node be a broker? That is to make it a peer-to-peer system. Would this be able to survive a network partition? I guess, I think we can, if you generalize this approach, then yeah, as you said, you may make each node as a broker node. Like, many, you can extend this like IPFS or something like that. Then I think, yeah, we can think about that way. We can fully decentralize the brokers in that way. And then, okay.
Yeah, so that's my question. So in the beginning, you said you are aiming for a more scalable approach than, for example, psync.
Yeah, psync.
So that's a broad claim, right?
Yeah, that's right. So if I have to explain more detail on psync, I thought it'll take some time, so I didn't do that. But in psync, for example, in psync, they're using Bloom filter actually in the name. So I think you can make it big enough. The name, you can make the name big enough using the Bloom filter, but I think there's a limitation on that first. So we cannot, extend the name
Okay.
unlimitedly. So there's the first scalability issue, and also even if it is a partial sync, I think, yeah, there's the first one, I guess.
Okay, thanks.
And the next one is on slide 17. It seems that it is requesting a manifest, need to parse the manifest and then need to request the individual segments, right? How is that defined as subscribing? Does it then automatically receive subsequent data in 17? So in 17, request a manifest, need to parse the manifest, that's right. And then need to request the individual segments, that's right. How is that defined as subscribing? Because it subscribed the data manifest. We call that as subscription. We receive the subscription, the published information using the data manifest. So we can, even if you have to check that periodically, but we call that a subscription. How is that? Okay.
Okay.
There's no automatic way for this one. We have to check that automatically. Periodically.
Yeah.
I think there's a current way of NDN. There's the NDN way for now. And is the chat being saved?
Yeah,
Okay.
that's another question on your presentation.
Okay, I'm copying. Okay.
No.
Okay.
Okay. Yeah, great. Are there any other questions? Okay, yeah, thanks again. Looking forward to the software release. And yeah, thanks for being at the meeting. We know it's not a convenient time for you.
Okay, yeah, thank you very much. Yeah.
Thanks. All right. So next, same time zone actually, is Guangdong Tai on NDN-based Ethereum blockchain, and I make you presenter. So welcome. Can you share your slides? Ah, okay, coming up.
All right. Can you hear me?
Yes, we can hear you, but we're not seeing your slides. We're seeing something else.
Oh, all right. Okay, can you see it? Can you see it now?
Not yet, at least not me.
Not yet. Hold on.
So the sharing worked, but you were not sharing the right window. Yeah, okay, now we can see it. Okay.
Can you see it now?
Yes, very good.
Right, can I start now?
Yes, please go ahead.
All right, the topic is NDN-based Ethereum blockchain. So basically, I'm going to explain how we design the blockchain system for the NDN network. And so we start with the motivation. So we believe that blockchain may have many potential use cases, especially when we think about the decentralized internet. And probably blockchain may play some important role. For example, we can see application like name resolution system or identity management, or even for the PKI system, we can use blockchain system. But right now, we don't have any blockchain system for the ICN. So that's the reason we want to develop the first blockchain system for the ICN, more specifically for the NDN network. And when we see the blockchain system on the IP network, we see some problem, especially at the transport layer, because as a data propagation traffic in the blockchain network is highly redundant. Usually we send multiple copy of the same data in the network. And we believe that the blockchain technology can take some benefits from the ICN. So we want to develop the first functioning blockchain on NDN in order to support the decentralized applications. And of course, we want to support the NDN-based blockchain research, because when we move the blockchain system from the IP network to the NDN network, we change the communication model. So basically, we may have some new problems. For example, we may have some new consensus protocol for the designed specifically for the NDN network, or we may have some security issues with the blockchain system over the NDN. And another reason we want to develop our blockchain system is we want to experience the development of the NDN application, and we want to see what kind of thing we need to change in order to have a better supporting of the blockchain like distributed systems. And obviously, we cannot develop our blockchain system from scratch. We have to base our development on some existing systems. So we have several options like Bitcoin or Hyperledger or Ethereum. So in the end, we select Ethereum because of several reasons. Because the first is that Ethereum supports the smart contract, and which may have many potential use cases. And currently, in the Ethereum ecosystem, there have been a lot of decentralized applications. And the Ethereum network, it has been working securely for many years, and the source code is very stable, optimized, and it is well supported by some big community. And also, the Interim platform is very popular for the academic research. And but how here I'm going to explain how the data is propagated in the Ethereum blockchain network. So basically, the blockchain system is a distributed, replicated system. So every node tries to have the same set of data. So everything has to be broadcast in the blockchain network. So usually they use the Gatship protocol to broadcast the data over the peer-to-peer overlay. So in Interim, they use the academia distributed hash table to construct the peer-to-peer overlay. And from the route of the academia, they're going to select several peers randomly, and then they try to iterate the TCP connection to those peers, and they are going to do state synchronization with the peers. So when a node have a new data, for example, like they have a new transaction or new blocks, they're going to send the transaction or send the block to the other peer. But if the data is small, the data is pushed directly to the other peer. But if the data is large, usually they push it to some small number of peers, and for the remaining peers, they just announce the identity of the data, and then the other peer have to request for downloading the data. So you can see that in this data propagation model, we have a lot of traffic redundancy, because many copies of the same object are sent and received on the network. And in the case that if you announce the data and the other node have to download it from you, so sometimes it can take very long distance to download the object, the data. So we can see some problems. We can easily see many problems with the transport layer of the blockchain network in blockchain system in the IP network. And so we want to design a blockchain system for the NDN network. So when we start to design our blockchain, we have several concerns. So as you can see that the data propagation in the blockchain system is similar to the data synchronization problem. And we already have several protocols such as the chronosync, phishing, or vector syncs. So our first question is whether we can use the protocol for our system. And the second question is whether we can use, do we need the peer-to-peer overlay for the NDN-based blockchain? So we analyze the protocols and we come to a conclusion that we cannot use the existing protocols. It's due to several reasons, because the first reason is that in a blockchain system, we expecting that node can come and leave, and we do not manage the membership of the node in the system. But in the existing protocol, for example, like chronosync, usually you need to manage the who is joining the group, and the reason is that because they model the state of the system based on the state of each individual based on the state of every member. So they need a membership management, and in the blockchain system, we cannot allow such kind of membership management. And the second problem is about these scalability issues. And because for example, in chronosync, you have to use the interest multicast. But when a node in the chronosync want to broadcast its state, it have to use it's going to send an interest message, and the interest message have to be multicast to every other member of the group. And in order to do so, all the NFT have to enable the multicast strategy. So we believe that is not a feasible assumption for the blockchain system. And the last issue is that the existing protocol was not designed for the system that have malicious nodes. For example, if a malicious node sends some invalid state, and then it can cause all the other node in the chronosync system to stop for state reconciliation. So we believe that in a blockchain system it's not acceptable. So we think that we cannot use the existing protocol for the blockchain system. And for the second question is whether we can, do we need to use a peer-to-peer overlay? And I think we still need the peer-to-peer overlay for the blockchain system, because in a blockchain system, when you receive a data, you usually have to validate the data before you propagate the data to the other peers. Because because we expecting that in the blockchain system we have some malicious nodes, and they can send the invalid data. So if they send the invalid data, the data are going to be blocked at the honest node of the network. So so how we designed our blockchain system for the NDN? So the assumption is that every node in the blockchain system must have a routable prefix, because in the blockchain node have to be a consumer and producer at the same time. So they must have a routable prefix. And in order to enable the in-network caching and internet aggregation, we need to name all the data object. We need the data object. We need to give the data object a globally unique names. And but and also the name have to be location independent. So if we have the name with location independent, how can we forward the interest to the producer? So in order to do so, we have to separate the object name from the forwarding information. So we're going to put the forwarding information in the forwarding hint of the interest. So we use the announce and pull data broadcasting scheme for broadcasting the data in the blockchain system. So basically, when a node have a new data, it's going to announce the identity of the object to the peer-to-peer overlay, and then the other peer, when they receive the announcement, they're going to request for the data directly from the announcer, and the node going to validate the data before forward the data to the other node. So invalid data is not from the whole network. So in this slide, I'm going to explain a little bit more detail about how the announce and pull data broadcasting works. So basically, in the figure, you can see that for example, when the peer 0 have a new data, like he has a new block or new transaction, you're going to announce the data to the other peer, for the peer 1 and peer 2, and he's going to use an interest packet, and he embed the object identity in the interest packet and send it to the other peer. And based on the announcement, the other peer going to create a name for the data packet, and they send the request to the announcer and to request the data, because because every data object have a unique identities, and all the interest going to have the same name. So we're going to have the interest aggregation. So announcer receives the interest, he's going to send the data back to the network, and the data is multicast to all the requester. So when the other peer receives the data, they have to validate it before announce to the other peer. Okay, so in this figure, I'm going to explain the idea a bit in more detail. So, for example, in this figure, we have a network of four domains, and we have one blockchain node at the attree domain. So it have a node name like this, attree/devnet Bob. And when he got a new block, he's going to announce the block to the other peer, for example, the Alice from UCLA. So he sends an interest. So in interest packet, in this interest packet, he have to include his identity, and I mean the announcer identity and the block hash. So when Alice receives the announcement, she can create a name for the data object and request the data from the announcer, because Alice already knows the mapping between the Bob identity and his and host name. So she can use that information to put it in the forwarding hint of the interest, so that the interest can be route to the announcer. So when the second peer requests for the same data, he going to get it from the NFT. So we implement our blockchain system on the NDN. So actually, we develop our system from the Go Ethereum official client, and because right now NDN community do not support the client library in Go language, so we have to develop a minimal Go NDN client, and we have to replace the peer-to-peer module in the existing Ethereum client by NDN-based peer-to-peer module. And we designed and implement all the blockchain, all the block and transaction broadcasting and chain synchronization protocols. And we actually we finished implementation, and we do some experiment on our implementation. And I think that our software is quite stable now. And in this slide, I'm going to explain how we do some performance evaluation of our blockchain system. So we want to compare the performance of our system to our blockchain to the IP-based Ethereum blockchain in terms of traffic use. So we set up a system of 5 domains, and in each domain we have from 5 to 20 blockchain nodes. And so in total, we have around 25 to 100 nodes. And we running the blockchain system, and then we send some transaction at a constant rate. And then we measure the upstream and downstream traffic at every node, and we taking the average of the traffic. And we calculate 2 ratios. The first one is we call the traffic redundancy ratio. So it's we take the traffic divided by the size of the blockchain, and so this number is the smaller is better. And the second ratio is we call it the catching ratio. Actually, it's the we take the downstream traffic minus the upstream traffic and divide by the downstream traffic. So this number is it's always smaller than 1, and the bigger is the better. So here I'm going to show some result of our experiment. So on the top we have 2 figures. Also on the left hand side is we plot the traffic. So you can see that in the blue line is the upstream and downstream traffic of the IP-based blockchain, because in the IP-based blockchain, the upstream and downstream traffic are the same. And the red line is for the NDN downstream traffic, and the orange line for the upstream traffic. And the purple line is the size of the blockchain. So you can see that there are a lot of reduction in terms of traffic use in the NDN-based blockchain. So if we take the ratio, we can see that in, for example, like in IP network, if we want to produce 1 megabyte of blockchain, we're going to we need to send around 9 megabytes of traffic and receive around 9 megabytes of traffic. But on the NDN-based blockchain, we only need to send around less than 2 megabytes of data and receive less than 4 megabytes of data. So in total, we reduce around 70% of the traffic on the NDN-based blockchain. And on the lower figures, we show the caching efficiency in the NDN-based blockchain. So on the left-hand side, we see the traffic, and you can see that the blue line is downstream traffic, and the red line is the upstream traffic, and the black line is the size of the blockchain. So in in the NDN-based blockchain, we are expecting that the upstream traffic is always smaller than the downstream traffic because of the catching effect. So if we measure the catching ratio, we can have the result around more than 50%. All right, so okay, I'm going to go to the some demo for our system first. All right, so okay, I'm going to show you the demo of our system. So basically, I have a system of 100 blockchain nodes running on 5 domains. Actually, I set up these 5 domains on 5 servers, and I'm going to run the demo on another server. And from this server, I'm going to create some blockchain network and connect to the existing network. Can you see my video? Okay. So can you see the video? Can you see it? No?
Sorry, I was. So you don't seem to be sharing any window right now. Maybe you have to set it up again.
All right.
Yep, something is happening. Yeah, you can see it.
Can you see it?
Yeah.
Yes. All right. So first, I'm going to start running the blockchain network of 100 nodes on 5 domains, and then I'm going to attach to one of the nodes to monitor the node. As you can see that when I connect to the node, I can see that the node right now have around 80,878 blocks. And then I connect to another node, and I can see that they have the same number of nodes, as you can see. And then I move to the another window. I start a new node. Okay, so is it not going to connect to the other node on the existing network? And it also now it did not have around more than one block more than the other node, so they need some synchronization. So you can see that now the block number are the same, and then I'm going to start another node. All right, now you can see that all the nodes have the same number of the block. And you can see the content of some block, and they must be identical. All right. So now I am going to create a brand new node. So let me delete all the previous data, and then here I'm going to generate a new node. So basically, we have to give the information of the first block, the genesis block of the blockchain, So we okay. So in order for the node to connect to the network, it needs to place information of one existing node. So we call it the boot node. So the boot node has the NDN name like this. So now we are going to copy the boot node to the data directory of the new node, and then we start the new blockchain node, and it start to connect to the network. And right now it have only a single block, so it have to download all the block from the other peer. So it usually takes several minutes to finish downloading all the block from the other peer. So in the meantime, I'm going to send some transaction to the network. So basically, I'm going to send 5 transactions to some node in the network. Okay, so then I can check these the pending transaction of in each blockchain node. We can see that we have 5 pending transactions. And let me send another batch of transaction. Now we send the transaction to another node, and we're going to receive the transaction. So now we have the 10 pending transaction, right? And now I'm going to send the transaction directly to one of the lower left node, and you can see that it's going to receive transaction. So I send 5 transactions to this node, and basically the other node going to request the transaction from this node. But you can see here only we have only 5 transaction requests. So it means that the interest was aggregate in the NFT. So the node is receive exactly only 1 request for each transaction. Okay, so now we have 15 transactions. And now I'm going to start mining on one of the nodes, because right now there's no miner in the blockchain network. So the transaction is not written to the block. So we have to start one miner so that the miner can create block and include the transaction into the block. So I'm going to start a miner. Okay, he's going to start to mine the new block, and it takes several minutes, several seconds. And all right, so we have to wait a little bit. Okay, in the meantime, I'm going to send some other transaction to the network. All right, and now if you look to the lower right corner, you can see that the node has finished synchronization. So okay, now this node has the same number of blocks as the other node, because he already finished synchronization. And okay, the miner already find a new block, and you can see that the other node had requested the block, and they fetch the block number 18,880. You can see that they fetch the block from the miners, and what you see here is you have only one request at the miner. It means that the request have been, the interest has been aggregated. All right, so I think that is for the demo of our blockchain system. All right, so let's go back to the all right, so do you see my screen now?
Yes.
All right, so in conclusion, we can see that in the NN-based blockchain, we can reduce traffic. And we plan to have more tests on the test network for the latency measurement, because right now we cannot measure the latency of the NN-based blockchain and compare it to the IP-based blockchain. So we plan to have that the more tests later, and we plan to publish our software as the open source package. All right, and one of the things that we are concerning is whether we put the announcement in the interest package, where we will be wondering whether it's an appropriate way to send the data in the ICN or not. So probably we're gonna have some feedback from the other guy who working on the NDN. And I think that is for my presentation. All right.
Thank you very much. That was really interesting.
Okay.
Thanks for preparing this demo.
All right.
It's really cool to see. Yeah, so we have time for say 1 or 2 questions. We're running a bit late. So I think this was really interesting. So in terms of the design decisions that you took for the protocol. So if there are no questions now, I think what would be really nice if you could maybe write up your design, maybe in something like a spec or a paper. It doesn't have to be a draft necessarily, but I think that would help people to understand it and yeah, have a good discussion with you.
All right.
But so in general, I think many people have been looking forward to this because, I mean, yeah, we always had the intuition that well, these ghosted protocols are really inefficient, and so an ICN-based approach seems to be suitable. And so yours is, say, yeah, one of the first, yeah, really experimental approaches. So that's really good that you really built the system and were able to test it. So it was really nice to see.
All right, thank you.
So I hope you are on the ICNRG mailing list, so that may be good for you to get more questions.
Yes, all right. I see a question about, do we have a paper on the Interim works? You mean the paper about our design of the blockchain system? Yes,
that's what I meant.
Yeah, actually, we are preparing the paper, and I think we will try to publish it very soon.
Great. Yeah, looking forward to it. Thank you very much again.
All right. Thank you.
Thanks. Okay. Yeah, sorry, running a bit late, but this was super interesting, and it's going to be interesting for the next presentation as well. So we have Todo as a Gava, also from a very inconvenient time zone. Apologies for not optimizing the agenda for that, I realize. Todo, I made you presenter.
Yes, sure. Okay, I will share my slides. Okay, can you see me?
Yes, we can.
Okay. Thank you for the introduction. Okay. Hello, so this is Toran Seras, so from Osaka University. So today's presentation is a joint work with the Osaka University and the UCL. Today's talk is the summary of our published paper, onion routing, which is published in the IETF transactions on network and service management of these areas. Okay, so our presentation focuses on the producer anonymity. So currently, so there are a couple definitions for anonymity. One is the consumer anonymity. The other one is the producer anonymity. So consumer anonymity means that the adversaries cannot run who requests some specific content. And so producer anonymity means that adversaries cannot run who publishes some specific content. So today's topics focus on producer anonymity. So which possible scenarios of these two types of anonymity is that the one is the privacy sensitive application like location-based services. The other is the censorship evasion. So maybe so our target is the censorship evasion and maybe location-based services. Okay. So in the literature, so consumer anonymity and the producer anonymity were addressed several studies. The most important one is the ANDANA, which was developed by UCI. So this is the this work was inspired by onion routing in IP. This is the maybe so Tora in at LDN networks. So CRISP is also the provides consumerity, but it's not onion routing, so it is the P2P based. So our work is extension to ANDANA. So as our provides produce anonymity through the NDN attribute-based signature address anonymity, producer anonymity. However, this study only handles the leakage only from these signatures. This is not insufficient to completely achieve the producer anonymity. So, in my talk, so first we briefly explain and then we explain how to do our producer anonymity protocol. ANDANA is the consumer anonymity routing for consumer anonymity. So ANDANA shows that this type of adversaries evade drop packets on compromised network entities routers to trace their origins. So tries to break the consumers and the producers. This figure shows the system overview of ANDANA. In ANDANA, a consumer chooses a series of two anonymized routers. A series of the anonymizing routers called the circuit. Then a consumer shares the secret keys, both anonymizing routers. This is the first step. The consumer issues internet packets whose name is encapsulated in multiple layers of secret key encryption around the circuit. It is very similar to the Tor. It's just onion routing. Then each anonymizing router decrypts the interest packet, then forward to the next anonymized routers. Packet is back to the consumer via the reverse process. So Andana is very similar to Tor in IP. However, Andana has the one good advantage over Tor in IP. Andana achieves a similar level of anonymity comparable to Tor with one fewer anonymizing routers. Precisely, Tor needs three anonymizing routers to provide the consumer anonymity. On the contrary, with Tor and just two anonymizing routers are enough. This is why Andana leverages the NDN. I mean that's in NDN, so NDN packets do not have any address, any IP address. So if the top anonymizing router checks the together. Okay, anyway, simply in Tor use three anonymizing routers. In Andana, this first of anonymizing router is needed because the interest and the packets do not have any physical IP addresses. So, okay. So we focus on this advantage of Andana. So we extend the Andana to onion routing protocol for consumer anonymity. So this anonymity in ND networks is very similar to receiver anonymity in IP network. However, this anonymity is a little bit different from the receiver anonymity in IP. So, we should consider the content name and signature. So anyway, so we carefully consider the adversaries. So in NDN networks, so adversaries can correlate content and its producer. These type of information pieces. One is the packet route. This is brought to the IP. So if adversaries are compromised, several anonymizing routers, so adversaries can reveal the route, then so identify producer. Another source of information is the content name and signature. So in NDN, the bindings between producer identity, name, and public key are established so that consumers can verify the provenance of content. Then so some of the private information inherently leaked from the signature or producer's name. So we designed the onion routing protocol for producer anonymity by taking into account these leakage of information. So the goals of the protocol are twofold. One is the designer system that achieves the producer's anonymity against adversaries who leverage content names, signature, and packet route. Anyway, the other goal is to we would like to leverage the NDA like Andana. So our approach is twofold. One is the design based on the hidden service in IP. So we prevent from leakage from the content and signature. Also, we want to prevent information leakage from the package. The other approach is the we leverage the anonymity offered by in-network. Maybe so we use the we leverage lies. We use the four-way handshake lies. Anyway, so lies provide some kind of anonymity. So we leverage this feature of the lies. So this is the overview of our protocols. Anyways, our protocol consists of five protocols, five procedures. The first one is the onion name. So the first pass mechanism is that a producer generates his pseudonym called the onion name. Onion name is the not identifier. I mean, it's not okay. Second one is the producer asks anonymizing router to act as a rendezvous point. The first of anonymizing router acts as a rendezvous point between the consumer and producer. So third one is the producer uploads his descriptor to several anonymizing routers called descriptor directories. This is similar. This is the same as the This is the same as the Tor hidden service in IP. Sorry. So first is the consumer who runs the onion name in some out-of-band way, downloads the descriptor. Then consumer knows onion name of the content which he wants. Then the consumer content name is the consumer issues content request specify the onion name through the rendezvous point. Then content is retrieved from the producer. So next several slides shows the details of the protocols. I will skip some of them. Okay, the first one is the onion name. Onion name is the structure is like this. So first component is the reserved word. This is the onion name. The second one is the hash values of the public key ID of the producer. third one is the suffix. Suffix, this is the content name. So publisher okay. Okay. Never reply. So anyways, so this type of name does not reveal information on the producer because it is not routable, not human usable. So this onion name is secure because it is the self-certifying. Okay. Next one is the rendezvous establishment. So the goal of the rendezvous point establishment is to anyway the producer asks them anonymous router to act as rendezvous point by sending her the onion name and self-certified signature. Then anonymizing router accepts it if hash names contained in the onion name is valid for public key ID in the subject case. So one of the problems is that the producers cannot send these elements with the standard interest data exchange. So anyway, we need some kind of the anonymity. So producers' routable name must be hidden to all other entities to achieve producer anonymity. So we leverage the RISE. So I will skip the RISE protocols. Then this is the procedure of the rendezvous point establishment. So this is the rendezvous point. So this four-way is the RISE. So a producer sends his name to the rendezvous point. Then rendezvous point sends the interest packets from the consumer like this. Then producer push the data. So in that case, we use the encryption keys. Then internet anonymizing routers does not know who sender or who receiver. By using the RISE, we provide some kind of the anonymity between the producers and rendezvous points. So we use this kind of mechanism to between the anonymized routers. Then, okay, we don't have so much time, so okay, we will skip the details of the protocols. So anyway, I skip the descriptor publication retriever. So anyway, after the encryption keys are set by the producer, anonymized routers, and rendezvous points, again the RISE. For example, the producer sends the first interest packet to the rendezvous point anonymously. The consumer sends the request to the producer. At that time, rendezvous point sends the second interest packet of the RISE to the consumer. Then producer push the contents to the rendezvous point, like the RISE. Then the result is returned to the consumer. And finally, acknowledgement returned back to the producer. So by using the RISE and encryption keys, consumer or advocates cannot know who are the producers. Okay. So anyway, so currently, so we are implementing the this protocol. So this is the sample of the preliminary evaluation of the performance. This slide shows the overheads of the encryption of the packets are not so large. Also, important of the our product anonymity protocol are twofold. One is the fewer hops. The number of hops is smaller than produce anonymity protocol in IP. The other is the our protocol is more resilient against predecessor attack in IP, predecessor attack than Tor in IP. So predecessor attack is the a very strong attack in onion routing. So if adversary is a couple of the routers, okay, so if a couple of routers are compromised by a consumer, linkability of client and server is broken. So in the Tor, in hidden services in IP, so the adversary compromise the two routers. Okay, so okay, I'm sorry. This is not so. In the Tor, so only one router. Okay, the adversary must just run a router. On the contrary, so in my protocol, so in our protocols, adversary must compromise two routers. This one, two. Then so for adversaries, it is difficult. It is more difficult for adversaries to compromise many routers. So our produce anonymity protocol is more resilient than predecessor attacks than Tor in IP. So currently, so we are implementing the this protocol on Sepro, which is provided by NIST. So, okay. So I spent almost a minute. So this is okay. That's the end of my presentation. Thank you.
Thank you very much, Toru.
Mm-hmm.
So there have been some questions on the
Sure.
chat, which
Sure.
are partially answered by Yuki.
Yeah.
So yeah, the first question was by Dave: is the onion name the same for everybody? And if so, can an adversary learn anything by seeing the request for the same onion name?
Okay.
So Yuki already replied. I'm not sure you can see the chat right now. But...
I will check. I'm checking. So. Yeah. So anyway, so okay. So we did not check the whether. Okay. I think that this the same name same name is used. Then so maybe so is not resilient against the frequent attacks. But so we did not check the whether protocol is resilient against frequent attack or not. So, other question?
Okay.
Yes, also we need some outbound mechanisms to send the onion. Yes. So we plan to use this some kind of the distinguished has table mechanisms, but we did not precisely design the such outbound mechanism.
Mhm. So just as a reference, I'm not sure you are aware of the CCNX key exchange protocol that was presented in ICNRG years ago. That could actually be used for setting up a TLS-like security context.
So currently, we use the very simple DP Hellman type of the protocol. So we can use the CCNX key exchange protocol, but we did not check whether we can use this protocol or not.
Yeah, okay, it's just a pointer for you. Great. Any other questions? Okay, thank you very much again. Appreciate it. And so we are moving on to our final presentation by Cheng Gunwan. And I am making presenter.
Yeah, hi Dirk, can you hear and see me?
Yes, very well.
Nice, great. Share. So, can you see my slides?
Yes, we can.
All right, then I will just start because I think we don't have that much time left. So thank you, Dave and Dirk, for having this slot on the call. And this presentation is mostly recap and a continuation of the work that we did together with Christian Amses, Thomas Schmidt, Matthias Wehlich, and me for the ICN20 conference, where we built a Web of Things deployment, an RFC compliant Web of Things deployment that also displays information-centric characteristics. And if you're interested in a more highly technical talk, then you can also look at the pre-recorded video that is, I think, hosted on the ICN conference website on this topic. So what does a Web of Things actually mean? For me, a Web of Things is a deployment where we have constrained IoT devices. They interconnect using a low power and lossy network, even in the multi-hop networks, to more powerful gateways. And these gateways have an uplink communication to cloud services. And of course, the paradigm that fits very well in this scenario is the REST paradigm. And there are like two very prominent protocols for doing RESTful deployments on the side, on the cloud side. So between the cloud and the gateway, we have HTTP using TCP. And on the constrained IoT and the gateway side, we use CoAP. And of course, how to secure such a deployment using transport layer security, where we use TLS for HTTP because of TCP, and we use DTLS for CoAP because of UDP. So deployment as this faces many challenges. I picked two of those and put on the slide. So one is the network resilience, and these deployments, there are many factors that can lead to degradation of the resilience itself. It may be cross traffic or radio interferences or other things like exhausted buffer space. And this leads to retransmissions on upper layers. In this case, for example, CoAP retransmissions, which then again lead to more network stress because of the added overhead, the packet overhead. And since we are using an end-to-end communication here in CoAP, we see that, of course, retransmissions have to traverse from the origin to the endpoint. So it has to traverse all the links again for each retransmission. Another problem is the end-to-end security. As soon as we have gateways that terminate security, we have to also include them into the trust infrastructure. So it gets more complicated to distribute the keys and to decide which gateway to trust or to not. And of course, especially in DTLS, we have this added overhead of creating or establishing a session for IoT nodes when they change endpoint information like IP address or ports. We saw, I mean, there were like many research papers in the previous years that show that information-centric properties, in this case, stateful forwarding, caching, and object security, can try to reduce the burdens of the problems we see and face in those deployments. For example, the stateful forwarding and caching, they shorten the request path and reduce link traversals on retransmissions. And the object security can help with the end-to-end security. And we don't need to have session establishments if the endpoint changes. So we have this paper at the ICN20 that I just mentioned, and there we try to figure out, okay, can we use the benefits of these ICN characteristics in co-app deployments? And we try to figure out the building blocks that we would need to build such a thing. And we came up with this list. So if you look deeper in the co-app communication model, then we see there's like a couple of methods that co-app defines, similarly to HTTP. So we have the co-app get method, put, post, update, delete, and more. Co-op get method is the method that has the highest similarity to an NDN or CCN model using interest data. So here would be a co-op get and the data that returns. And co-op also allows to have retransmissions for the requests, and returning data would be an acknowledgement. But co-op also allows to have retransmission for responses, which need a separate acknowledgement from the requestee. When we look at the standard RFC of co-app, we see that they define an entity called proxy that forwards requests and that relay back data packets or responses the same way. So it's very similar to what NDN is doing anyway when forwarding. So we basically store state in the proxy and can send responses back on the path. And proxies also have the ability to do caching, which of course is very handy because NDN also is doing that. And then we have object security for co-app. This is relatively new RFC called OSCORE. It's from last year, July, I think. Provides authenticated encryption and has methods or features like confidentiality, integrity, request response, strong request response binding, and is doing replayability tries to disallow replayability attacks. And so with these building blocks, we asked ourselves, okay, what can we do with, how can we form such a deployment? And what we did is we took a multi-hop topology and we configured each constrained IoT device in this topology to be actually a co-op proxy that forward requests. And then we enabled the caches and, of course, encrypted and authenticated all the messages using OSCORE. So on the right side, you see this figure where you can see a co-op get message that originates from the red node. This get message is received by a forwarder. It creates state. It then sends out a new get message to the next forwarding node. And this repeats until we hit the content producer. The content producer produces the content, which is then stored on each hop in the cache. If we have a loss, a packet loss, then we do the request retransmissions, and this looks very, very similar to what NDN is doing. We have caches along the way, and the caches can fulfill the requests. The request. So if you look at the network stack itself, how it looks like, we can see on the left side the CCNX and NDN stack. In this case, we use an adaptation layer. Here it's ICN-LoWPAN. And on the right-hand side, you see the new network stack, or I mean the IETF envisioned network stacks for the IoT using CoAP, based on UDP, IPv6, and 6LoWPAN. And on the application layer, we have now CoAP using proxies and OSCore. And what we now do is we basically rebuild the things that we had on the network layer for the CCN and NDN stack on the application layer. And now we, since CoAP is using URIs to request and to return content, we have forwarding based on names, which is also a similarity to CCN and NDN. But we have, of course, we have to be careful because in CoAP we don't have static content, so a name or a request can return different content, for example, different temperature values. Here's actually a bonus thing that, or something that surprised me when I built the system and did the experimentation. I looked in the PCAP files and I saw that actually the CoAP packets got much smaller, and I asked or looked at the PCAP files and tried to find out why. And the interesting thing is that IPv6 compresses IP source and destination addresses if they are linked local addresses. And I used linked local because we have this chain of forwarders, proxy forwarders. So we don't need to use the global IPv6 addresses, but the linked local addresses. And if you use a linked local IPv6 linked local address that derives from a MAC address, then the 6LoWPAN even omits the full IPv6 addresses, the source and destination address, so we can save 32 bytes. So there are benefits if we build a CoAP that has these characteristics. We have improved resilience, and we showed this in the paper. You can look at the paper or the video for the plots and information. It has a reduced latency, and it is, of course, there's a location independence of data like in NDN. But then we asked, do we also gain like insights that we can use for the CCN or NDN world? And this is something that we not really highlighted in the paper itself, but we summarized a little bit, and things that we came up with. Okay, there's an early deployment chance if we have an ICN or a CoAP that's like an ICN. We could actually use caching strategies or forwarding strategies that are like designed for an NDN. Why not use that in CoAP deployments which are already running? And then there are two features that CoAP implements, and also like mentions in the RFC. For example, there's like the response acknowledgements. So what if we can transfer that from the CoAP to NDN? What if we do retransmissions and acknowledgements for data packets also to make a more robust system? There are some initial measurements that we did that show if we lose requests, or if we actually we could use early acknowledgements for retransmissions, for request retransmissions, to stop the retransmission on each hop for requests. But then we have, then we need response acknowledgements, because then we can send back the response as soon as we have the data, instead of being pulled by the retransmissions. But of course, then we need the response retransmission and acknowledgement in case that gets lost. And there's also the efficient cache revalidation using an ETAG in CoAP. It's very similar to what HTTP is doing. So if we have a cache with stale cache entries, and an interest tries to get a content from that cache, the cache or the node can actually ask the producer of that content if the data is still fresh, and it can do so by sending an ETAG, and the content origin then just replies with yes or no instead of sending back the full data. So we also have ongoing efforts, and we are mostly interested in the multicast because CCNX and NDN inherently support the multicast. And we might be able to also transfer that to CoAP itself. NDN is, of course, using request aggregation and response deduplication. And why not you also use that for CoAP? I think should be quite easy to do this for content that is static, but it's probably more complicated for content that changes. Yeah, so then the next step would be to evaluate group communication. I mean, the protected group communication, for example, using group OSCORE, and see how that works out in in this kind of CoAP deployments, and how does it affect the caches of protected or the cacheability of protected messages. So that was quite quick, and we still have time for questions, and if there are any questions.
Yes, absolutely. Thanks a lot, Shane.
Yeah. Thank you also.
So that's so I would really appreciate that you picked up the nice discussion at the ICN conference and came back with a follow-up presentation. That's exactly what we had hoped for. So thanks, that was really nice. So are there any questions? So while people are still thinking about the questions, so I will repeat my comment from the conference. So so if you can go back to slide 6, for example.
Here.
No, it wasn't 6. Maybe move forward. So just one where you show the network. Maybe this one is fine, actually. Yeah, this one. So I'm not sure we are really comparing apples to apples here, because it seems to me that in this CoAP network here, you have something like a pre-configured proxy chain. So in any approach, you would probably, I mean, as for example, in your other paper, NDN in the wild for IoT, you would have maybe a forwarding plane that is able to find next hops itself and so on. That probably would be difficult in CoAP, I guess, unless you re-implemented all the ICN semantics.
I mean, that's true. I mean, at least for the evaluations of this paper, we used, like you said, a pre-configured forward chain. But I think it should be quite easy to have a discovery protocol that tries to. I mean, there are, for example, discovery protocols in CoAP itself using like a resource directory. I'm not yet sure how we would be able to integrate this into these kind of deployments. But I don't see huge showstoppers. I mean, yeah, I mean, there, of course, we need to think about this, whether it would work to have a dynamic topology management to find the correct proxy, the forward proxy.
And then
I have one question.
Yeah, okay.
To what extent do you think the immutability properties that we tend to hold dear in ICN affect some of these design decisions?
Yeah, that's a good question. So, I mean, of course, it has a huge impact on the caching, because if we say that we now allow, for example, data that is mutable, we can't really do caching. I mean, or at least we have to have versions or timestamping to request old state of the data. There's also the problem of, at least for the protection, the OSCORE, for example, puts counters and sequence numbers into the security envelope. So also there, it would be kind of hard if we have mutable content, because then we have different signatures and whatnot. So I think I mean, the system that that is there, that is in the paper, of course, works out of the box for content that's immutable. As soon as we go to mutable content, I mean, I think that we need more thoughts, or yeah, need to make more. Maybe there might be also be more discussion on this. I'm also not yet sure if. I mean, it's probably, yeah. I mean, it's of course use case dependent. NDN is doing that apparently. I mean, without mutability in co-op, we need that. Depending on the use case, I'm not yet sure which is the way to go.
Okay. And so regarding your potential future directions, I mean, one outcome of this could be that in your end you basically re-implement the ICN node behavior mostly, but you're just using co-op as a different packet format or convergence layer if you want.
Yeah.
So is there still value? I mean, I think the value then is that okay, you can run this over co-op networks.
Yeah. I mean, this re-implementation, I'm not yet so sure about, because everything we used up until now is RFC compliant. So, I mean, it's already there. The building blocks that co-op provides us allowed us to build such kind of systems, and why not use these things? I mean, I don't think that when the designers of co-op made the specification, I don't think that they had the intention of using, for example, proxies on every hop of the network.
No.
This is just something that, I mean, makes the system very similar to NDN, but it is still protocol compliant. Yeah, I mean, I'm not yet sure what we need. I mean, what extra stuff we need to, if you want to keep, if you want to make a further more like ICN, what else we need? Yeah, let's see. I mean,
Yeah, I was more thinking about what you could pitch as opposed to what you could add.
Right.
Yeah. Yeah.
I mean, a lot of what you talked about with retransmissions and hacking data seem to me to be oriented toward reclaiming buffer space in the intermediaries. Whereas hop by hop retransmission of interests in ICN kind of obviates that, and your cache management is based only on arrival of data.
That's true. Yeah, I mean, there's this one use case I try to highlight here. Retransmission also costs, of course, bandwidth, and they also induce radio interference. If we can reduce that, why not? But then we have the problem. I mean, as you said, then we have to have data acknowledgements. But there's currently no way in NDN. I mean, there's no data type, for example, to do this.
Okay. Yeah, it's interesting. I think.
Well, I would mention it's easy to produce hop by hop acknowledgements for NDN, right? The question is, what would an end-to-end acknowledgement? Doesn't really make any sense, because then the producers know things like consumer count and, what does it mean when to acknowledge a data that may have reached, 100 consumers? What does that acknowledgement mean? It seems to have all the same problems as multicast acknowledgements, explosion problems.
Yeah. I mean, was it actually? Yeah.
Well, okay. I mean, I think this is an interesting direction, and I mean, we are looking at this IoT space from different perspective. I mean, the other perspective is certainly to build something from the ground up that does what IoT applications need without any legacy. And so I think it's going to be interesting to kind of compare these two tracks at least. Okay, good. Thanks again, Schenk.
Yeah, thank you also.
And 1 second. Yeah, okay, this brings us to the end of our agenda. Yeah, thanks everybody for staying for so long. We actually didn't expect that we really fill these 3 hours, but we did. And next time we should plan in a break if we take that long, or split it up into 2 meetings. But in any way, that was really interesting. Thanks everybody for presenting and for participating in the discussion. Just a few things. Yeah, let's continue using the mailing list for technical discussions as well. So I think there were probably some questions raised today that we didn't answer, and so I think that's still a good way to discuss this. Other than that, we used to have an effort for organizing draft reviews, so like an online spreadsheet. I think Dave and I will have to revive this and send a message about that. Future meetings. So yeah, as you can imagine, we're probably not going to meet face-to-face anytime soon, so there will be more online meetings. If you have any ideas, also feedback regarding today, so how to do things differently, please talk to us. So one thing that we hope we'll do soon is another focused meeting on Flick, as Christian mentioned in the beginning. And so yeah, we will announce this, of course, and everyone would be welcome to attend that. Okay, other than that, thanks again, and yeah, please stay safe, everybody, and hope to see you again soon.
Thanks, everyone.